Ever feel like you're playing storage Tetris with your Kubernetes apps, constantly shifting blocks around and just hoping nothing crashes? You're never quite sure if you've given them enough space to breathe. Well, today we're diving deep into a pretty fundamental challenge when it comes to running applications on Kubernetes, figuring out just how much storage those digital building blocks actually need.
Yeah, it's like trying to decode your application storage appetite. You want to keep them happy and performing well, but also avoid overspending on resources you don't actually need.
Exactly. And that's what we're going to unpack today. We'll be focusing on Kubernetes persistent volumes, those PVs you often hear about, and persistent volume claims, or PDCs, and how they play a crucial role in determining the right amount of storage for your applications.
Right. We've been digging into a bunch of articles and guides on Kubernetes storage to get a good grasp on best practices, common pitfalls, and some real-world examples. So hopefully, by the end of this deep dive, you'll feel more confident about managing storage for your stateful applications in Kubernetes.
That's the goal. Less head scratching over storage calculations, fewer unexpected outages, and maybe even some cost savings along the way. So why don't we kick things off by addressing the elephant in the room, or rather the elephant in the cluster? Why is getting storage sizing right so crucial in the Kubernetes world?
Well, it really boils down to three main things. First, you have application stability. Think about it. If an application suddenly runs out of storage, what happens? It can crash, it can start behaving erratically, and nobody wants that, right?
No, not at all. Unpredictable behavior is the enemy of a smooth running system. What else is at stake here?
Then there's the whole data integrity piece, which is absolutely vital, especially for things like databases, where you're dealing with, well, valuable data. If you don't have sufficient persistent storage, you're putting that data at risk.
Right. Data loss or corruption is a nightmare scenario for many applications.
Absolutely. And then, of course, there's the cost factor. Over-provisioning means you're essentially paying for storage that's sitting there idle, not being used. It's like having a giant empty room in your house that you never use, but still have to pay rent for.
Makes sense. It's about finding that sweet spot, that Goldilocks zone, where you're not wasting resources, but you're also not putting your applications or your data at risk. And this is where persistent volumes and persistent volume claims come into the picture, right? They're like the foundational building blocks for how storage works in Kubernetes.
Exactly. So think of a persistent volume, or PV, as a chunk of storage that lives within your Kubernetes cluster. It could be, for instance, a volume provided by your cloud provider like AWS or Azure, or maybe it's a network storage device. Now, the thing is, your applications don't actually directly interact with these TVs.
They don't. So how do they get the storage they need?
Well, that's where persistent volume claims come in, those PVCs. An application, let's say a database, creates a PVC, which is basically a request for a certain amount of storage with specific access requirements.
So the application is saying, hey, Kubernetes, I need 10 gigabytes of storage, and I need to be able to read and write to it. Can you hook me up?
Exactly. And the cool thing is that the application doesn't really care where that storage comes from. Kubernetes takes that claim, that PVC, and finds a suitable persistent volume that matches the criteria and connects them.
So this decoupling, this abstraction between the application and the underlying storage, that's a pretty powerful concept, right? It gives you a lot of flexibility.
Yeah, it does. The application, through its PDC, is basically saying, I need this much storage, and it needs to have these access permissions, but it doesn't have to worry about the underlying storage technology or where it physically resides. This makes it a lot easier to, for example, move applications between different environments or even different cloud providers.
That makes a lot of sense. Now, to make this whole process even smoother, I know we have these things called storage classes. How do they fit into this storage puzzle?
Storage classes are a really handy way for cluster administrators to define different types or tiers of storage that are available within the cluster. So imagine you have, let's say, a fast storage option that's backed by SSDs for applications that need really high performance, and then maybe you've got a standard option that uses regular hard drives, HDDs, for applications that are less demanding. And these options can have different cost profiles as well, right?
Of course. So when you create a PVC, a persistent volume claim, you can actually specify which storage class you want.
That's right. And based on that storage class, Kubernetes can then automatically, dynamically provision a PV, a persistent volume, that fits the bill.
Okay, so instead of having to manually create a PV every time a new application needs storage, Kubernetes can just handle that automatically based on the storage class. That sounds like a huge time saver.
Oh, it definitely is. This whole dynamic provisioning thing is like the preferred way to do things in Kubernetes these days. It's so much more scalable and efficient than the old way of static provisioning, where you had to pre-create all the PVs and then have applications claim them.
And I've seen examples where you can specify some pretty detailed parameters within a storage class, right? Things like which provisioner to use and even the specific type of storage you want from your cloud provider.
Absolutely, you can get quite granular with it. For example, a storage class for those fast SSDs might have a parameter that says, use the AWS EBS provisioner, and then another parameter that specifies, I want GP3 volumes from AWS.
All right, so we've got this foundational understanding of how storage is provisioned and claimed in Kubernetes. But now let's shift gears and talk about something that's directly relevant to everyone listening. How do you actually figure out how much storage your applications really need? Because clearly, a simple web server isn't going to have the same storage demands as a massive, busy database.
Absolutely. Different applications have wildly different storage appetites, and understanding those individual needs is key to getting this right. It's not a one-size-fits-all situation. So let's start by looking at databases, because those tend to be some of the most storage-hungry applications out there.
Yeah, databases, I mean, for many applications, the database is where the crown jewels are kept, right? That's where the valuable mission-critical data lives.
Exactly. And for databases, persistent storage isn't just, a nice to have. It's absolutely essential. You need that data to persist, even if the pod running the database restarts or crashes. So when you're trying to figure out how much storage a database needs, you've got to think about things like the current size of the data, how fast that data is growing, how many transactions are happening, those IOPS we mentioned earlier, and what your recovery requirements are in case something goes wrong.
So a database that's constantly being bombarded with transactions will need not only enough raw capacity, but also storage that's fast enough to keep up with those demands. And as we touched upon earlier, not all storage is created equal in that regard.
Right. Some applications, especially databases, need storage that delivers high IOPS, meaning it can handle a lot of input-output operations per second, and also has low latency, so there's minimal delay when accessing data. This often means you'll want to choose a storage class that provisions storage on faster technologies like SSDs or even NVMe drives, which are even faster.
And for managing these stateful applications like databases, it's worth mentioning stateful sets, right? They're kind of a specialized tool in Kubernetes for handling these types of workloads.
Oh, definitely. Stateful sets are a Kubernetes controller specifically designed to manage applications that require stable network identities and persistent storage that sticks with each replica. So if you have a database with multiple replicas for redundancy, a stateful set makes sure that each replica has its own dedicated storage that follows it around.
Okay, that makes a lot of sense. Databases, high demands, fast storage. Now, let's switch gears a bit and talk about those workhorses that are serving up all our web content, web servers. What are their typical storage needs?
Yeah, so web servers often need storage for things like static content, your images, CSS files, JavaScript files, all that stuff. They also need storage for logs and maybe even temporary files or session data, although session management is often handled by external services these days.
Right, so we're talking about storing a website's assets, tracking its activity, and potentially managing user sessions. But is there anything unique about the storage requirements for web servers in a Kubernetes environment?
One big difference compared to databases is that you often need shared storage for web servers. This typically involves network-attached storage solutions where multiple pods can access the same shared file system, though sometimes this can mean a bit more latency compared to dedicated local storage.
Shared stores, why is that so important for web servers running in Kubernetes?
Well, think about it. You often have multiple instances or replicas of your web server running to handle traffic and ensure that your website stays up, even if one replica goes down. And if all these replicas need to access the same set of static files or write to a central logging system, you need a way for them to share that storage.
Makes sense. If each replica had its own isolated storage, keeping things synchronized would be a nightmare.
Exactly. So for web servers, you'll often see the need for a storage solution that supports read-write-many access, which is often shortened to RWX. This means that multiple pods can read from and write to the same storage volume simultaneously.
I've even seen some specific examples of web applications that explicitly require RWX access.
Oh yeah, absolutely. We came across an example where Burke Suite Enterprise Edition, for instance, explicitly states that it needs RWX access for its deployment.
Interesting. So it's not just about how much storage a web server needs in total, but also about how many pods need to access it and what kind of permissions they need. And I would imagine that the speed at which that storage can deliver those website assets, that throughput, is also pretty crucial.
Absolutely. You want your website to load quickly, especially if you have large images or videos or if you're getting a lot of traffic. So storage throughput becomes a key performance indicator for web server deployments.
Right, let's wrap up our look at different application types with one more common category, message queues. queues. These are essential for asynchronous communication in many modern architectures. So, how do we approach storage considerations for message queues in Kubernetes?
Message queues, much like databases, often rely on persistent storage to make sure that messages are delivered reliably and don't get lost if something happens to the queue.
Right, you wouldn't want a critical message to vanish into thin air just because a pod restarted.
Exactly. So you've got to think about factors like how many messages you expect to be flowing through the system, how big those messages are on average, and how long you need to keep those messages around, based on your application's needs or any regulatory requirements you might have.
I imagine that in a high throughput messaging system, storage performance becomes pretty important.
Absolutely. If you have a ton of messages being processed, the storage needs to be able to keep up with that rate of writes and reads. We even saw an example of a message queue deployment that was using a 10 gigabyte PVC, showing just how important dedicated persistent storage is for these workloads.
All right, we've talked about some common application types and their storage needs in a general sense, but now let's get practical. For you, the listener, how do you actually go about figuring out the right amount of storage for your specific workloads in Kubernetes? Where do you even begin?
That's a great question. And it's a question that a lot of people struggle with. I think the first step is to really understand your application's current storage footprint. Take a look at your existing databases, see how big they are. Check the size of your static content repositories for your web servers. Look at how much storage your message queues are using. Basically, take inventory of what's already there.
Right, it's like establishing a baseline, getting a snapshot of your current situation, but that's only part of the picture, right? We also need to think about the future.
Exactly. Once you have a good grasp of your current usage, you need to start projecting how your storage needs might change in the near future. And this often involves looking at things like how much you expect user activity to increase, whether you're going to be ingesting more data, or if you have any new features or initiatives coming up that might impact your storage needs.
I remember reading about how the Prometheus monitoring system actually has a pretty specific approach to estimating its own storage needs. Can you tell us a bit more about that?
Yeah, so for certain types of applications like Prometheus, where data generation follows a pretty predictable pattern, you can get a bit more quantitative with your estimations. And in the Prometheus documentation, they actually provide a formula that you can use. You plug in your desired retention time for metrics, the rate at which new data is coming in, and the average size of each data point, and it spits out an estimate for how much storage you'll need.
That's a pretty neat example of a more data-driven approach, but for many applications, I imagine predicting growth is a bit more, well, art than science.
Definitely, you have to use Riv intuition, historical data, and good judgment. And it's always a good idea to build in a buffer, some extra space, just in case you have an unexpected surge in data or your workload spikes temporarily.
So it's better to have a little wiggle room than to be constantly running up against your storage limits and risking those crashes and performance issues we talked about earlier.
Exactly. And the other thing to remember is that this isn't a one-time decision. You need to keep monitoring your storage usage over time and have a plan for scaling your storage resources if you need to.
So it's an ongoing process, not a set it and forget it kind of thing. This naturally brings us to thinking about the longer term. How should we approach planning for our Kubernetes storage needs beyond the immediate future?
Thinking long-term with storage means anticipating how your data might grow over months or even years. And this requires digging a little deeper into those historical trends, understanding how your users are interacting with your applications over time, and factoring in those business growth projections. Don't just think about the next quarter, think about the next year, or even further out.
So it's about adopting a long-range view of our data landscape. What are some of the specific things we should be considering in this long-term planning process?
Well, one thing that's really important is to think about data retention policies. How long do you need to keep certain types of data around, either for legal reasons, compliance reasons, or maybe just for your own internal purposes? These policies can have a huge impact on your storage needs, especially in highly regulated industries like finance or healthcare.
I can imagine that those industries have some pretty strict rules about data retention.
Oh, absolutely. And if you have enough historical data, you might even want to explore using some predictive modeling or trend analysis tools to get a better handle on your future storage demands. But even if you don't have fancy tools, just extrapolating from your past trends can give you some valuable insights.
Right. Looking at past patterns can be a useful guide, even if it's not a perfect predictor of the future.
Exactly. The key is to remember that capacity planning is an ongoing process, not a one-time event. And as your data grows, you'll also want to think about the cost implications.
Right. Storage can get expensive, especially as those data volumes start to climb. Are there any strategies for managing those costs over the long term?
Yeah, definitely. One common approach is to use data archiving and storage tiering. So for data that you don't need to access very often but still need to keep around, you might want to move it to a cheaper, slower storage tier. This can help you save a lot of money without sacrificing your ability to access that data if you need to.
So it's like having different levels of storage, a bit like those different tiers of service you get with cloud providers.
Yeah, exactly. It's all about optimizing your storage costs while still meeting your data retention requirements.
Okay, so we've made some initial estimates, we've thought about long-term growth, but how do we actually know if those estimations are on target? How do we know if we're giving our applications just the right amount of storage without going overboard?
That's where monitoring comes in. It's absolutely crucial to keep an eye on how much storage your applications are actually using in real time. It's like having a fuel gauge for your storage.
So continuous monitoring is key. What are some of the specific things we should be looking at when we're monitoring our Kubernetes storage?
There's quite a few important metrics to keep in mind. Obviously, you want to track the total provision capacity of your PVCs, how much storage you've allocated, but you also want to see how much of that storage is actually being used and how much free space you have left.
Right, you want to make sure you're not getting too close to the edge of the cliff.
Exactly. And then you want to see how fast your storage consumption is growing over time. Are you using more and more storage each week, each month? That can give you a clue as to whether you need to adjust your storage plans.
It's like keeping a pulse on your storage usage, understanding those trends. Are there any other metrics we should be watching?
Well, in addition to those capacity-related metrics, you also want to keep an eye on some key performance indicators, those KPIs everyone's always talking about. Things like IOPS, remember those input-output operations per second? That tells you how quickly your storage can handle read and write requests. You also want to watch throughput, which is essentially how much data you can move through your storage per second. And then there's latency, which is the delay between requesting data and actually getting it.
And are there specific tools or methods for monitoring these metrics in a Kubernetes environment?
Oh, absolutely. Kubernetes itself gives you some basic tools. The Kubernetes dashboard is a good place to get a visual overview of resource utilization, and you can use the Kubestal command line tool to dig deeper into the details of your PVs and PVCs.
So the built-in Kubernetes tools provide a good starting point.
Exactly. But for more in-depth historical analysis, you'll probably want to use a dedicated monitoring system like Prometheus. People often use that in combination with Grafana, which is a great tool for visualization to create dashboards and alerts. And of course, if you're using a managed Kubernetes service from a cloud provider like AWS or Azure, they usually have their own monitoring tools that can give you a lot of insights into your storage usage as well.
So we have a whole toolbox of options for monitoring our storage, but just collecting this data isn't enough, right? We need to actually do something with it.
Right. It's all about being proactive. You want to set up alerts so that you get notified if something's not right. Like if a PVC is getting close to its capacity limit, or you're seeing a big drop in storage performance, you want to know about it right away. And don't forget those performance metrics like IOPS, throughput, and latency. They're just as important to monitor as the overall capacity.
Absolutely. You could have plenty of storage space left, but if your storage is slow, your applications are going to suffer. Which brings us to another important point. How do the performance needs of our applications actually influence our storage choices in Kubernetes?
That's where you start getting into the finer details of storage management. You have to match the storage you choose to the specific needs of your applications. So for example, if you remember those transactional databases we talked about earlier, they often need a lot of IOPS, a lot of read and write operations happening very quickly. That means you'll probably want to choose a storage class that provisions storage on high-speed media like SSDs or NVMe drives. On the other hand, if you have an application that's doing a lot of data processing, like analyzing large data sets, maybe throughput is more important than super low latency.
So it's all about choosing the right storage for the job. And I know cloud providers offer a whole menu of persistent disk options. How do we navigate those choices in relation to performance?
Yeah, the big cloud providers like AWS, Azure, Google Cloud, they all have various types of persistent disk storage with different performance characteristics. For example, AWS has its Elastic Block Store, EBS, and within that you have different volume types like general purpose SSDs, provisioned IOP SSDs, and so on. Azure has its managed disks, and Google Kubernetes Engine, GKE, has its own persistent disks. It can get pretty confusing.
It sounds like it. So how do you decide which one to use?
You have to look at your application's specific needs, your budget, and the performance guarantees that each option provides. And remember, the way you access your storage can also impact performance, especially if you're using shared storage with that read-write many access we talked about. When multiple pods are hitting the same storage volume over the network, it can introduce some latency.
So for really critical applications, getting the performance right might be the most important factor, even more important than worrying about capacity at the outset.
Absolutely. If your database is stars for IOPS, it's going to slow down your whole application, even if it has terabytes of storage space available. And of course, you also have to keep cost in mind. You don't want to pay for super high performance storage if your application doesn't actually need it.
It's all about finding the right balance, isn't it? Not overspending, but also making sure your applications have what they need to perform well.
This whole conversation highlights the delicate balancing act involved in Kubernetes storage management. We're trying to avoid those two extremes, over-provisioning and under-provisioning. Can we talk a bit more about the consequences of those two pitfalls?
Yeah, both over-provisioning and under-provisioning can come back to bite you. Over-provisioning, at first glance, might seem like the safer option. If you have everything tons of storage, what could go wrong? But the problem is, you end up wasting money on storage capacity that you're not actually using. And it can actually make it harder to spot performance problems in your applications.
Because you're masking the symptoms by throwing more resources at the problem. Exactly. There are techniques like thin provisioning, where storage is allocated on demand rather than all up front, that can help litigate that waste.
So over-provisioning isn't just about wasted money. It can also lead to a false sense of security. What about under-provisioning? What kinds of dangers are lurking there?
Under-provisioning is where things can get really messy really quickly. If your application runs out of storage, you're looking at crashes, data corruption, performance going down the drain. And in Kubernetes, if a PVC asks for more storage than is available, it can get stuck in this pending state. And any pods that rely on that PVC might not even start.
That sounds like a recipe for downtime and headaches. So it really is about finding that sweet spot, giving your application enough storage for their current needs, and a bit of room to grow without going overboard.
Exactly. And this is where a feature like dynamic resizing becomes really valuable.
Ah, yes, dynamic resizing. This sounds like a game changer for managing storage more flexibly. Tell us more about how that works.
So dynamic resizing basically lets you increase the size of your PVs on the fly without having to do a bunch of manual work or take your applications offline.
And this is a fairly new feature in Kubernetes, right?
It became a stable feature in Kubernetes version 1.24, so relatively recent, but it's already making a big difference.
Okay, so it's a powerful tool, but I imagine there are some prerequisites, some things you need to have in place to actually use dynamic resizing.
Right. First, your storage provider and its container storage interface, CSI driver, have to support expanding volumes. And then the storage class that your PVC is using needs to have a setting called allo volume expansion turned on.
So it depends on both the storage infrastructure and how you've configured your storage classes.
Exactly. But once you have those things in place, the actual process of resizing a volume is usually pretty straightforward. You basically just edit the PVC spec and change the requested storage size to whatever you need. Kubernetes then takes care of talking to the CSI driver and expanding the underlying PV.
And does the application automatically see that extra storage space?
Sometimes you might have to do an extra step to expand the file system on that volume, but often Kubernetes handles this automatically, or you can trigger it by restarting the pod that's using the storage.
So it's a pretty seamless way to adapt to changing storage needs without having to go through a lot of hoops.
It is, but there's one important caveat. Kubernetes generally doesn't support shrinking PVs. Once you've made a volume bigger, you usually can't make it smaller again. So it's often a good idea to start a bit smaller and then use dynamic resizing to grow as needed.
That makes sense. It's easier to scale up than to scale down. Well, this has been a really thorough deep dive into the world of Kubernetes persistent volume capacity planning. What are some of the key takeaways we want our listeners to remember?
I think the biggest thing is to really understand your application's unique storage needs. Don't just guess. Do your homework. Plan for both your current needs and your future growth, but don't go crazy and over-provision everything. And keep a close eye on your storage usage with monitoring.
Monitoring is key, both for capacity and performance.
Absolutely. I remember that dynamic resizing is a powerful tool for adapting to those changing needs.
So for those of you listening, think about your most storage-intensive applications. What are their peak demands? How are you tracking their storage usage? Could you benefit from dynamic resizing? This deep dive is just the starting point, but hopefully it's given you some food for thought and some practical strategies to improve your Kubernetes storage management.
Absolutely. And we always love to hear from our listeners. If you have any stories about your own experiences with Kubernetes storage, or if you have any burning questions, please share them with us. Might even feature them in a future deep dive.